When we are looking for extrema of a function, we must consider three types of points. Points where the derivative is zero, a stationary point. Points where the derivative does not exist, or the endpoints of the domain of definition. Consider the function absolute value of x. The graph looks like that. It has derivative equal to 1 for positive x, no stationary point. It has derivative equal to -1 for negative x, no stationary point, no extrema here, no extrema here. But just from the graph you see that it has a nice minimum which is both local and global at 0, but no derivative at 0. You see? So this is a nice example of a continuous function which does not have a derivative at the point 0 and which has an extremum at a point other than a point with 0 derivative, namely with no derivative. This is a very, very important case. Consider another function. Y is absolute value of sine of x. Sine of x alone, without absolute value, looks like that. Just for the interval from 0 to 2 pi, because it is periodic, so everything interesting that occurs here will occur elsewhere, and vice versa. But now the absolute value will change the graph. From 0 to pi, the function values are positive, so the absolute value has no effect. But for x values between pi and 2 pi, sine is negative, and taking the absolute value of the negative results will make the positive results. So this will be not part of the graph, but it will be mirrored up this way. And similarly here. So if we consider just x between 0 and pi, then y is sine, and the derivative is cosine. But cosine looks like that, and if we find the stationary points, that means we solve the equation y derivative is 0, then cosine of x is 0 in this interval as the solution x is pi half. And as the derivative changes from positive to negative, the function changes from increasing to decreasing, and from this it has the local maximum. Now for x between pi and 2 pi, we can remove the absolute value, but then we must change the sign. The function is minus sine of x. So the derivative is minus cosine of x, and minus cosine of x in the interval between pi and 2 pi. Cosine looks like that, and minus cosine looks like that. And again, this equation in this interval has a root in x is 3/2 of pi. And the derivative again changes from positive to negative. So the function changes from increasing to decreasing, and it has again maximum. Well, and in between these two maxima, there must be at least one minimum. Indeed, there is a minimum, which is easy to find from the graph. Namely, at x is pi is a local minimum. But this minimum cannot be found using the condition y derivative is 0. because at pi the derivative is not 0. The derivative is nothing. It does not exist. It's not. This function has no derivative at pi. Actually, at no integer multiples of pi. So when points where the derivative does not exist, when points where there is no derivative, when these points exist, where the derivative does not exist, we must consider these points also as possible candidates, possible danger points for an extremum to occur. And then the situation at the end of the domain of definition. Let me give you two simple examples. Y is square root of x. The graph looks like that. And again, there is no stationary point. There is no point where the derivative is 0. Because if we write it as x cubed 1/2, then the derivative is 1 over 2 square root of x. Namely 1/2 of x2 minus 1/2. And when we want to solve this equation, this is a fraction with definitely not 0 numerator. Numerator is 1. So this fraction is never equal to 0. For all positive x, this derivative is positive and the function is increasing. Well, it goes up. No minima, no maxima for positive x. But you can see that at the end of the domain of definition, namely at 0, we still have a minimum, even a global minimum. So points at the end of the domain of definition must be also considered as possible candidates for extrema. And a similar case is the function arc sine. The graph looks like that. The function is increasing in its entire domain of definition. So no extrema in inner points. But what about the endpoints? -1 and 1. Yeah, from the graph we see that at -1 we have a minimum, at +1 we have a maximum. Just to write the derivative, you know that the derivative of arc sine is 1 over square root of 1 minus x squared. And again, this expression is never equal to 0 because this is a fraction with non-zero numerator. But there are points in the domain of definition where this derivative does not exist. The domain of definition is the closed interval from -1 to 1. And this expression can be evaluated in the open interval only. So at -1 and +1, the derivative does not exist. So how to conclude this case? We have a function, and we find all the possible candidates for extrema. That means points where the derivative is equal to 0, points where the derivative does not exist, and points that are at the end of the domain of definition, if such points exist. Well, and then in the inner points, in the stationary points, where the derivative is equal to 0, we can consider either the sign of the first derivative close to the point or the second derivative. And then we find extrema in this kind of points, and then we must check the values at the points where the function has no derivative or at the ends of the domain of definition.